We have with us our next speaker, Mr. Ken Zhang, who is the Chief Architect of the Huawei Kunpeng Big Data Technology, Director of the Data Application Lab, and the PMC Chairman of the Open Lukang Community. He has 20 years of experience in big data development and has worked on global big data projects at Thomson Reuters and IBM. He joined Huawei in 2018 and took charge of Huawei's big data technology planning and technical competitiveness building. He envisions a simplified big data platform in the hope of higher system and human efficiency. He leads the overall development of the analytics engine to support both AI and BI use cases requiring 100+ millisecond response time through standard interfaces. In his current role, he provides leadership and guidance to R&D members in Toronto, Shenzhen, Chengdu, Bangalore, and Dublin. He will speak on TransJIT, data-driven specialization of compiled queries. Mr. Ken Zhang, over to you, sir.
Thank you very much for the introduction. And it's an honor to join this conference. Can you hear me okay?
Yes, sir, but could you turn on your video if it's as possible?
Sure, yeah. I think there's a permission issue that I'm not able to start my video.
Oh, okay.
It says you cannot start your video because the host has stopped it.
Okay, let us just try to see if we can fix that. Can one of the hosts start the video, please? Right click and say start video on Mr. Ken Zhang's name. Santosh, if you're available.
Here we go. I think I just started my video. Can you see me now? Or?
Right. No, sir. We're seeing a dark screen right now with an emblem on it.
Oh, here we go.
Oh, there you go.
Okay, here we go.
We can see it. We can see.
Yeah, we can see you now.
You can also see my screen, right?
Not yet. You can start sharing again. I think we had stopped sharing, so you could start sharing now.
Sure.
We are good to go, so we can see. Yes, sir.
Okay, that's great. A little bit of a glitch here. I guess it's normal for any anything that is online, right? So again, thank you very much for inviting me, and it's an honor to speak at this very famous and prestigious conference. So my talk today is going to be share some of the information about a project that we've been working on since earlier this year. It's called TransJIT, Data-Driven Specialization of Compiled Queries. The name is a little bit different. I think we messed up the name a little bit, but it's the same content. So I just want to talk a little bit about the trend in data analytics for improving the performance. I think codegen and JIT is one of the technique people have been using to improve performance. A lot of open source data analytics engines and commercial engines are leveraging codegen and JIT for better performance. But codegen and JIT, it's not easy. You have to know a different set of APIs. You have to know very low-level APIs, and it also introduces another layer of indirection because you are basically generating code to generate the running code that is processing the data you want to process. And there are also other problems like the computing resources are becoming more and more fragmented, and there are various different computing resources available. It becomes heterogeneous with FPGA, GPU, and like NVIDIA DPU are all coming out, and it all impacting how we are generating the code and JIT the code. So again, codegen and JIT being used widely, but it is not easy. It's very expensive technique to use. So here is another slide that kind of describing how we look at this. So there are code that is either generic, you can rewrite it in high-level languages to process the data, or they are also code that is very difficult to generate, but they have much higher performance. So they are both easier solution and fast solution, but there's not really a solution that is both fast and easy. So the way that we are doing it is a new framework that hoping that it will be easy to cheat the code, and at the same time allow people to write the logic in high-level languages. So the requirements that we are having here is basically hoping that we would make the whole analytics engine development process a lot easier than before, instead of using the low-level APIs such as LLVM to generate the code and JIT compiling the code. We are hoping that you can just write the logic in high-level language in C. And we are also hoping that it will be support other capabilities like security and further optimization. Being security meaning that being able to protect the data information and privacy information end to end without developers to code all of the security features into the logic. So for example, the TEE trust zone capabilities that can be embedded into the operators that we are implementing. And we are also hoping that the framework will be able to dynamically adapt to the different heterogeneous hardwares. So these are the requirements that we are trying to handle. So as the as a solution to this, we created a JIT framework. We call it OmniJIT. And the idea is to use annotation to annotate a target function that we want to optimize. And this annotation will provide information on which functions you are trying to JIT compile at runtime. And we also support annotation in place, so that you can just put the annotation side by side with the C or C++ code. We will show you an example later. Or you can put the annotation outside of a file. Our annotation preprocessor will be able to pick up all of those annotations and combine it with the original source code, and then try to JIT compile the code together when we try to build the final application. Another thing that once we have the target function, we also provide a way to do something called the context prepper. The context prepper is a tool that will be able to analyze the context that your application is running in. And the context, in this case, very often it will be the parameters that you pass to your program. So for example, you pass a piece of data to process for your program, and that piece of data could be the context that the context prepper would try to do profiling to find out the cardinality, to find out the nullability and the distribution, also the data layout before the program is started. And then those information will become the context for the JIT. So the next thing is that the OmniJIT preprocessor would basically embed the context prepper into the original function, and it will be invoked before the original function is invoked. And then the function that we are trying to optimize will have a proxy function called JIT proxy ingested into it. And the JIT proxy will basically making decisions at runtime, deciding whether it's a good idea to JIT compile the original function or not. If it find out it's going to have performance improvements by JITting based on a cost model, then it will JIT compile. Otherwise, it will just use the original model. Another thing that as part of the framework is that we would be able to have a branch-specific optimization path. So for example, if we tested our framework with a SQL engine, and we would be able to apply different optimization paths for different operators to get the best machine code out of it. So as part of this framework, we provided an adaptive optimization pipeline that allowing specific optimization process to each operators instead of having one single compilation optimization pipeline. Such when you use GCC, we're going to specify -02 or 03, and that same optimization pipeline will be applied to everywhere, all of the code. Now we are able to apply different optimization pipelines based on the operator, based on the context that the operator is running in. And as a result, we will have a JITable application generated at the end. And when we start the application, it will basically, as I mentioned, it will try to run a context prepper, which will analyze the input parameter and populate the context and provide a context to the JIT proxy, where it would decide whether it's a good idea to JIT compile the target function or not. So here's an example of, there are two types of annotations. One of them is the function annotation, where we annotate a function and indicate which parameters can be specialized, can be optimized. So if we are invoking a function directly and there's no intermediate state between that, then we can use the input parameters directly as the parameter for the specialization. So in this case, we have an example function that is multiplying two matrices, and there are three parameters indicating the dimensions of the matrix that we are trying to multiply, and those dimensions will be used for specialization at runtime. So as indicated by the specialized annotation. And the specialized annotation, you might want to ask that, what is that? The C++ program doesn't have that. It's actually a macro that we define, and you can just attach it in front of a function that you are trying to optimize. So that's very similar to a Java annotation. And it's very easy to use. It's just added to there, and it doesn't require any special compiler to process it. The only thing you need is add another step into the original build pipeline to invoke our annotation processor. So this, again, as I mentioned, it can be further enhanced by something we call the context prepper, and I will cover context prepper later. So once we have the specialized annotation to a function and run the annotation preprocessor, there are a couple of things that we will do. It's basically ingesting a lot of different code into the original function. The original function will be replaced by this. The first thing we will ingest into the code is that we will ingest the cache lookup. So if a function has been specialized with the same parameter in the past, then we will try to look it up from the cache, because it takes time to JIT compile a function. By looking it up, we'll be able to execute a function a lot faster. And then if we don't find it from the cache, then the next thing we do is that try to start specializing the value of the parameter. So for example, if the three dimensions of A, B, and C is 400 by 400, 400, then we will basically replace the parameter with a constant. And once you specialize the function with the constant value, it will give us a lot more possibilities to optimize the function. So the next step is basically specializing the parameters to a fixed value. And then after that, we will JIT compile the code. And then at the end, we will execute it. So basically, we will look up the function from cache first, and then try to simplify the original function by fixing the value of the parameters. And then once we fix the value of the parameters, it will give us other possibilities. For example, constant propagation And there are a lot of other calculations that we can potentially invoke by or triggered by the by this specialization. So this is the overall flow of the JIT compilation inside of the JIT proxy. So here's an example of the a benchmark of what we can achieve here. We are not measuring the performance by the time because it's actually pretty difficult to the computer can be impacted by the scheduler, and you're not able to get the time very accurate. Although overall it might give you an idea of how fast it's performing, but it will not give you exactly how much it's improved. So instead of using the time, we are using the number of instructions that is executed. So we compare the original function with the JIT function, and here you can see that the red is the JIT function, and the blue ones are the original number of instructions that is executed by the simple matrix multiplication. We tested with the 400 by 400 matrix, and 800 by 800 matrix, and also 1600 by 1600 matrices. We also tested with a different number of threads when we run it in parallel, how that would impact the performance. As you can see here, there's a pretty big performance improvement. In average, it's about 40 to 60% of performance improvements in terms of instruction count. So here, just I want to give you another idea of why this is actually improving the performance. In the data analytics world, it's very often that we have to handle data that we don't know the type ahead of time. Use SQL as an example, and use sum as an aggregation aggregator as an example. So if we have something called select sum column 1 from table 1, for example, the sum aggregator actually have to process different data types ahead of time, and it's very often there's control flow in the implementation where it will be checking if the type is int, I'm going to do it this way. If the type is flow, I'm going to do it in another way. So in this case, the ahead of time compiler will generate a flow very similar to what I have here. This is normally the flow that will be generated by the ahead of time compiler. But by OmniJIT coming in, specializing the parameter, we will probably know that the type, let's say the type is an int, then we will be able to actually remove the other branch here. And by removing the other branch, we will know that we do not need the if statement here or not. And then the top graph will be able to simplify into a graph below. And we will be removing a lot of control flows from the machine code that is generated. So this is just an example of what the parameter specialization would do for us. There are other specializations that we can potentially do. For example, data layout. There are other operators that need to handle all kind of different data layouts. And by specialization, we will be able to specialize the code to a specific data layout, and would allow us to remove a lot of control flow from this. Some other examples that of optimization is algorithm selection. So by having the cardinality, for example, in the code, we will be able to potentially select different hash algorithms for the operators, and we might be able to select different ways of memory formats to improve the performance. And for example, the hardware is also would allow us to pick when to kick in vectorization. So another thing that I want to mention is context annotation. As I mentioned that sometimes the context is not directly known. So the input parameters can be used to extract further information to optimize the application. Something that we are doing is that by using the context annotation, we specify something we call context prepper. And the context prepper will basically use the input parameter to find out what data you are trying to process. And then it will extract information such as layout information, cardinality information, distribution information, also the type information that the job is trying to process. And then those information will be provided to the JIT proxy. And the JIT proxy will be able to use those information to simplify the function that that is running as part of the data analytics job. And here's a simple example omni context annotation. And that again, this omni context annotation, it is a macro, and using this we can specify a context prepper. It's just another function, and this function will be invoked before the overall job is started to populate the context. Here's another example where how we can specify the context prepper function, and then here we will be basically passing in the context into the final into the operator. And I'm using a hash aggregation operator as an example, where we have put it into the one of the engines that we are working on. So just want to also mention that the OmniJIT is a technique that is part of a bigger overall function called Omni Runtime. And inside of the Omni Runtime, there are 5 major components, where we have something called Omni Cache. It is a relational cache instead of file block cache that is very popular in the big data world. For example, Alexio is another block cache that people have been using. So we designed something we call a relational cache, Omni Cache, that provides much higher hit ratio than block-based cache. And inside of this Omni Runtime, there's also an Omni Vector, which is a columnar in-memory format to enable SIMD operations. And OmniJIT and operators are the focus of this talk. We also have Omnidata that is handling the collaboration between the compute layer and the storage layer to do near data processing and being able to push down the SQL operators into the storage layer. And the data transport layer called Omni Exchange is something that is leveraging RDMA to improve data exchange during the analytics job execution. So we actually integrated the Omni Runtime with an engine called OpenOken, which is a SQL-based data processing engine. It is a virtualization engine allowing you to process data coming from different cloud, different region, in different formats. And here we use the Omni Runtime and the OmniJIT to optimize all of the SQL operators that is contained in the OpenOken project. So this just giving an idea of where we are using this. And here is another performance benchmark that we are doing. It basically try to use different data layouts and different data types and different cardinalities of the data to measure the performance of different operators. Here's an example of hash aggregation operator where we can see from 30% to about 60% of performance depends on the data layout and the cardinality. Another example is the order by, where it is actually performing much better than the original operators that is in our engine. And again, it's ranging from 30% to 60% of performance improvements here. So those are the previous 2 slides are at the operator level, and this is the end-to-end performance where we can see ranging from, because the TransJIT is improving the computation performance. And when we look at the end-to-end performance, there are a lot of I/O involved. And the I/O part hasn't been really improved by our framework yet. So you probably see that the end-to-end performance benchmark is actually smaller than, the improvements is smaller than at the operator level, but we're still seeing about 10 to 30% performance improvements end-to-end for TPCH Q1 and Q5. We have more data available, but we just didn't put it here. But anyone who are interested are welcome to reach out to me, and we will be happy to share those data with you. So one last thing to share, I guess, is the where we are going with this. So in the future, we are hoping that Omni Runtime and TransJIT will become the common big data runtime. And we are not only integrating Omni Runtime with the OpenToken engine that we are working on, we are also integrating it with engines like Spark and Hive. Probably will be the next engine that we are looking into, and we are hoping that it will not only providing faster data processing, also will be providing us more secure data processing by adding security related capabilities into Omni Runtime. So this is everything that I want to talk, and I'm open for questions. Thank you.
Hey, Ken.
Yes.
So it was a great talk and great listening to you. And all of that improvement without really using the crystal ball. I wonder what you would do when you have the crystal ball. So you would be able to predict and just do a compilation right before using it. So I have a few questions for you.
Sure.
From the audience. So in a complex big data application, unless we JIT all the operators in a query and reduce the overall instructions, it is really difficult to achieve performance benefits, as the data movement between the off heap to on heap itself might start causing extra overheads. So how are the operators being considered and developed for different hardware and execution engines?
That's a very good question. Actually, that's exactly the problem that we hit during the integration in a real engine. So yes, it's going to be a problem that if you have to switch between on-heap and off-heap memory all the time. So what we do is that we look at, because an execution plan will be divided into stages, and then we only use Omni Runtime when we able to execute the whole stage on Omni Runtime. That way, we'll be able to reduce the memory exchange between on-heap and off-heap memory. And this is exactly the same problem that we hit both with OpenToken engine and Spark. And in both of the engines, we leverage the same approach to make sure that unless all the operators can be executed on Omni Runtime, otherwise we would just leave it as is. Okay,
great. And also there's another question, and trying to get your view here. So OmniVec and OmniJIT seems to be similar to some open source projects like Apache Arrow for columnar format and Gandiva for the SIMD. So where OmniVec and OmniJIT has the improvement as an over and above the open source projects?
Yeah, that's a great question too, actually. We were trying to use Apache Arrow at the beginning, and I think that's a great project. There are a lot of adoptions of Apache Arrow, and Gandiva is another project. I think we learned a lot from it. But we feel that Gandiva seems to be pretty, I'm not sure how active it is. So we decided to we can create another one here. And the what we did it here is that in OmniVector, we added memory management into it. So because in the C++ world, memory management is a huge problem. So what we did is that we created something that would allow you to add a scope to all of the vectors that are created inside of that scope. So each SQL execution will be allocated within scope. And once the SQL execution finishes, we will basically destroy the scope. So it's very similar to the JVM, where you have some capability of memory management there. So that's one thing that we did, so that it will be a lot easier to manage the memory allocation. And if sometimes, and we all make mistakes, sometimes we do have memory leaks in our operators. And with this scope-based memory management, we will be able to ensure that there's no memory leak during the execution that is not caused by the OmniVector. So that's one thing. The second thing we did is the OmniVector has it has a memory pool inside of it. We actually have some data comparing OmniVector and Apache Arrow performance with the memory pool. In the OmniVector, the allocation and the release of vectors becomes a lot faster. It's compared to Apache Arrow, the performance about depends on the operation, but I think it's at least 30 to 40% faster than the than OmniVector. Than Apache Arrow. Another thing in the future that we are looking into is to make OmniVector self-JITable. Basically, whenever we create an OmniVector, and once we know the cardinality and the distribution, we will try to also dynamically JIT the OmniVector code so that it will be specific to a data layout, will be specific to a data type.
Sure, great. And Ken, one final question for you. So what are the considerations for fusing operators? Can any set of operators be fused to form a meta operator?
Oh, great question, actually. So yes, that's something that we are also looking into right now. It's in the pipeline. So we are looking at the operators that are inside of the same stage and potentially fuse them into a big operator. So there are two options for us. Either fuse the operator logic into one single tight loop that will potentially reduce the cache miss during the execution, or we can potentially just run the operators one by one, process them in batch. So there are pros and cons there. The first approach, putting everything into a tight loop, would provide us probably it will reduce cache miss, but it may not give us the best way to leverage SIMD operations versus the second approach where we process them in batch and run the operators one by one. It will probably give us better performance when it's possible to vectorize the operators. Another approach that we are looking into, and this is actually the approach that we think might be the best, is a hybrid approach where we have a tight loop processing a batch and we divide the input data into batches. This is probably, I think this is so far the most promising approach that we are looking into right now.
All right, great. Great to have you here, Kenjang, and I'm sure it's pretty late for you at home. And over to you, Anvit.
Thank you very much.
Thank you so
Sorry.
much, Mr. Ken. Well, I would like to let all the members of the audience here know that as we speak, Mr. Ken is in Toronto. It is 4 a.m. there. He stayed up just to deliver this amazing session to all of us. Thank you so much for that landslide of information and insights that you provided through the session. A big, big, big thank you to you from all of us here. Thank you so much.
Thank you. Glad to be here.